I'm here in the Lake District. I'm meant to be walking in the Fells, but it's pretty rainy, so I'm going to talk to you about a number. Matt and James wrote to me saying they want to do a project about a mega number, so people's favourite number bigger than 1,000,000. And I've chosen a number which I'd like to tell you about, which is 906,150,257. 906,150,257. And in order to tell you why I really like this number, I need to do a bit of a run-up. So I want to tell you about a conjecture that was suggested in 1919 by George Polya, called Polya's Conjecture. We don't know if he actually claimed he thought it was true, but certainly it's gone down in the sort of literature as Polya's Conjecture. And it's very simple, although I'll need to unpack this statement a bit. But here's the statement in simple terms. Most integers have an odd number of prime factors. That's it. You have to think a little bit hard to realise why that needs some unpacking. First of all, there's a problem with the word most. If we're going to talk about integers, there are a lot of them. As this project with the mega number implies, that once you've gone past 1,000,000, there's still infinitely many to go. So the idea of saying most integers is kind of nonsense when you realise you're talking about infinity. So we have to unpack what we mean by most, and what I mean by most in this case is if you pick a value, let's say n, then most of the integers up to that n have an odd number of prime factors. That would be a sort of technical upgrade to the intuitive version of the conjecture. And then we also have to figure out what we mean by counting prime factors. So let me show you a couple of examples of counting prime factors to see what I mean. So examples of prime factor counting. Let's say 10. 10 has prime factors 2 and 5, because 10 is 2 times 5. Therefore, I'm going to say fairly uncontroversially that 10 has 2 prime factors. That's it. If we look at 20, which is otherwise known as 2 times 10 or 2 times 2 times 5, I'm going to say that has 3 prime factors. Although if you're going to count it differently, you might say it's got 2 distinct prime factors because it's 2 squared times 5. So it's only 2 and 5 involved. But for the sake of this counting setup, we're going to count prime factors, not distinct prime factors, but prime factors. So if 2 appears twice in the prime factorization, we're going to count it twice. Let's check some other examples. If I pick 24, let's see what's that. It's going to be 2 times 2. That gives me a 4 times 2 times 3. I think that's 24. 2 times 2 is 4, times 2 is 8, times 3 is 24. So the number of prime factors of 24 is 4. 4 prime factors. And remember, the conjecture said that we're looking for the odd or evenness of the number of prime factors. So, for example, 10 has an even number of prime factors, 20 has 3, so it's an odd number, and 24 has 4, so an even number. And Polya's conjecture says that most numbers, up to a given point, have an odd number of prime factors. And it's somewhat surprising that that might even be possibly true, because what should favour them having an odd or even number of prime factors? Now, there are lots of other sort of interesting conjectures about numbers of factors. For example, the only numbers with an odd number of factors, not prime factors, but an odd number of factors, are square numbers, and that's quite interesting. But we're talking about prime factors here, and the conjecture just says most numbers have an odd number of them, if you count them repeatedly. So if 2 times up twice, you count it twice. First of all, let's establish a way of counting this. So what I could do is actually use what they call the louvre function, which gives you a +1 if you get an even number of prime factors, and a -1 if you get an odd number. And if you do the sum of the louvre function, or the summatory louvre function, or the louvre sums, however you want to call it, then you'll keep a running track of how many up to that point have had an odd or even. So if we're negative, we've had more odd numbers, and if we're positive, we have more even numbers, and if we're at 0, we've had exactly equal numbers of both. So what we're essentially saying for Polya's conjecture is that the summatory louvre function is always negative, or at most 0, because that would give us a sharper definition of what we mean by most as well, which we've tightened up slightly already. But when I say most, I'm going to say more than 50% up to a certain value. And this was posited by Polya back in 1919, and so for 40 odd years everyone kind of thought it was true. And let me show you a little glimpse of why we thought it was true. So I'm going to show a little video of the summatory louvre function, which remember is going up 1 for an even number and down 1 for an odd number of prime factors. And you'll see it starts wiggling around. So let me just show you the video of this. So it's bouncing up and down, really jaggedy, and it has a few surprises in there. I've let this run to 1,000, and I'm going to pause the video there. And you can see that we hit 0 a few times early on. And if you check the first few values of the louvre, you realise that it does balance out to be half of them are even prime factors, half of them are odd number prime factors. And then very quickly, after zigzagging out, it seems to end up negative and stay there. With one possible exception, you can see on the graph here at 586, it goes back to 0, it climbs all the way up there, and then it heads off down again. So if we keep running this video all the way up to 10,000, I think around this one, you can see it's really spikily jagged. It's kind of got a self-similar fractally look to it. There's some interesting consequences from that. Go and look up the Riemann zeta function if you want to see a connection with the Riemann hypothesis in this. But it's always negative. So far, up to 10,000, the Summatory louvre function is always negative, which means Polya's conjecture is true up to 10,000. Now, just about 10,000 you could check by hand. It takes quite a long time. I wrote a little Python script to do that animation, and with modern computers you can run scripts to higher numbers quite quickly. So let's have a look at a script running up to, I don't know, let's say 10 million to see if Polya's conjecture is true that far. So Louvre's sum up to 10 million. This is running much quicker than before. You can see it's still got that jagged, spiky look to it, and occasionally gets close up to 0. But to be honest, most of the time, although it's bouncing up and down, it's heading more and more negative. And as you speed up here, we're already at, like, what is that, 1 million we just crossed there? It's going further and further negative. It does seem to be going up and down, and as I mentioned before, that is to do with the Riemann zeta function, and look up the connections on Wikipedia or Wolfram if you want to go and explore that. But it's definitely still negative all the way. And this is what led Polya to conjecture that maybe it's always negative. Now, we've only just scratched the surface of the infinity of integers here, but we're running this up to 10 million, so there's a lot of them, and I don't think Polya was in a position to calculate that far by hand. And even if you do, with a computer and a Python script, you realise that it's always negative, or at most 0 early on, a few times. So most of the numbers have an odd number of prime factors up to that point, because that negative count is outweighing the positive one. But we haven't checked all the numbers. And why am I making a video about it? Well, you've already guessed why I picked that number at the start. 906,150,257 is the first time Polya's conjecture fails. Now, this was discovered in 1980. I mentioned earlier about this being pondered as a conjecture for 40-odd years, and 1980 is longer than 40-odd years from 1919. So actually what happened in 1958, 39, 40-odd years after the conjecture was written down by Polya, a guy called Hazelgrove proved that it was false. Now, he didn't do that by finding the smallest one. He did a technical proof that there was a counterexample. There was a point where this Summatory louvre function went positive, i.e. there was a point where there were more even numbers of prime factors than odd at some point. And he proved that it would happen, or he estimated the first counterexample to be somewhere in the region of 10 to the power 361. 10 to the power of 361. This is an absolutely mind-bogglingly big number. He didn't pin it down, he said it was roughly there. And he was right. But that still leaves the question, if it's false, there must be a first time it was false, and that was the bit that was found by a guy called Tanaka in 1980. He found that the number 906,150,257 is the smallest counterexample for Polya's conjecture. At that point, there is, at 906,150,256, there is precisely an equal amount of even numbers of prime factors and odd numbers of prime factors. And you go one beyond it, and it crosses the territory into more of them are even numbered. It's the first time, and it's way down the list. Let's see a little animation of that. So what I did this time was, because I knew what was about to happen, I told Python in my script, don't do all the way, but just do like 1 million before that critical place and go 1 million after. And you can see what happens when we look just 1 million before that. So the function is kind of holding steady around negative 1500. That means basically there's an outweigh of odd number of prime factors of about 1500 more than the even numbers. We're already at 905,500,000. But we're clucking up slowly towards the number I said at the beginning of the video. And as we cross 906 million, you begin to start thinking, well, this is maybe closer to 0 than it's been for a long time. And there is a crucial point coming just, where is it? It's, there it is, it crossed. And actually it crossed again, and crossed several times, and then for a region, it's staying really positive. It's gone way beyond 500 positive. And this is the first time it's gone anywhere near that. And then it goes back down again, and you think, well, was that it? And it's shooting off way down negative 1,000 now. This little region was a surprise. The nice thing about it is the first counterexample doesn't happen until 906,150,257, but then there's a whole load of them. The whole region around 906 million where the summatory Louvre function is positive. And then it goes on negative again. And there are all sorts of unanswered questions. Does this keep crossing backwards and forwards infinitely many times? Go and investigate. Does anyone know? This is a nice example of what you need to be careful with in mathematics. Just because a statement is true for the first 10 million numbers you've checked does not mean it's always true. And this is a really good example where the first counterexample is way down the list. So far down the list that you probably wouldn't check that far unless you knew there was a reason to check that far. And that's a danger in mathematics. Just because you've checked lots of examples does not mean it is true in general, which is why mathematics does concern itself with proof. The idea that we can't check enough numbers to prove something when you're asking about an infinity is a dangerous thing in mathematics. And it led to, this is an example of something which a guy called Richard Guy called the strong law of small numbers. Now, there is a famous bit of mathematics called the weak law of large numbers, which a lot of people think of as the law of averages. When you do things enough times, it tends to go towards a mean. And this is a kind of joke reference to the opposite effect. The strong law of small numbers is basically Guy saying small numbers can't do enough. The formulation Wikipedia puts it as there aren't enough small numbers to meet the many demands made of them. If you look at small numbers, you'll probably get the wrong idea. And when I say small numbers, even looking up to 906 million, in this case, is not enough. Although that's a lot of them, there are infinitely many more to go. So the small numbers are unusual because they're the first ones, and quite often they are misleading, and we have to get proofs for general cases, otherwise we get misled by what the early numbers do if we're looking at general things. And that is then why I've chosen as my mega number 906,150,257, because it is the first and smallest, therefore, counterexample to Polya's conjecture. I'm just going to say thanks to Matt, who's offered to edit all my bits of footage, because while I'm in the Lake District I don't have time to get my editing software out, so thank you, Matt Parker. If you want to make your own video about a number bigger than 1 million, upload it with the tag MegaFavNumbers, and James Grime and Matt Parker will add it to their playlist.